All right. So the last topic that we are going to cover in chapter 1, I think this is the last topic, is distance measurement. So how do we measure distances out in space? Well, I mean, we know the distance between the Earth and the Sun. That's 93 million miles. What is the name of that distance, that 93 million miles? What do we call that? I mean, what is the name of that yardstick, 93 million miles? It is one what?
Astronomical unit.
Yes, it's one astronomical unit. So it's 93 million miles. How can we possibly measure it? So how do we know these distances? And then when I say that the distance out to the closest star is 4.5 light years, how does anybody possibly know that? That's what we're going to briefly talk about right now. So the basic principle of measuring distance is as follows. Um, we'll start with this simple example, and then we'll see how we can extend this to astronomy. So suppose you are standing at this location, and you want to measure the distance out to this tree over here, which is on the other side of the river. And let's say you don't want to swim across the river. You want to somehow do it just without getting into the water, right? So how can you do it? Well, you can do it by making a couple of simple measurements. One is you can um, you can have a telescope and sight this tree, right? So you're standing directly across the river from the tree at location A. Now let's say that you move a certain distance, you move from A to B, and then you turn your telescope and sight the tree again, which means that you point your telescope directly towards the tree again. And you also measure what angle you need to turn your telescope in order to see the tree, right? So you now have this triangle. uh, the locations A and B were the two locations from which you pointed your telescope towards the tree, and you moved from A to B. There's there's no problem in measuring the distance from A to B. You don't need to cross the river for that. So the two pieces of information that you have are, you know, this length from A to B. Let's say you measured this length, and you also know this angle that you needed to turn your telescope to look at the tree from location B, right? Now, there is an interesting property of triangles, a mathematical property of triangles, which you might or might not remember from high school, that for any triangle, if you know two angles and one side of the triangle, then you can figure out everything about that triangle. So for any triangle, if you know any two sides, if you know any two angles, and any one side of the triangle, if these values are given, you can figure out everything else about the triangle. You can figure out all the other angle, you can figure out all the other sides, everything, anything that you want, you can figure out. So we can use that property over here in this triangle that we have on the right, the triangle ABC. Let's just call this point C. We do know one side and we do know one angle, right? And we also know the other angle. This is 90 degrees, so we know that as well. So we know two angles and one side, which means in principle we can figure out everything else. We are mostly interested in the side AC. That's the distance to the tree. Um, we can figure that out. I'm not going to get into the formulas of how you would figure it out, but the important thing is that if you know two angles and one side of any triangle, you can figure out everything about that particular triangle, right? Now, how do we, okay, and this becomes even easier if you have isosceles triangle. This is a typo, this should be isosceles triangle. Does anybody know what an isosceles triangle is?
A triangle with two equal length sides.
Exactly. If you have a triangle with two equal length sides, that's called an isosceles triangle, then the requirement becomes even simpler. So if you just know one side, you only need to know this angle at the top. Because if you know this angle at the top, you can easily figure out what these two angles are. How would you figure out these two angles if you know the angle at the top? What do the angles of a triangle add up to? What's the total number of degrees the angles of a triangle add up to?
180 degrees.
180 degrees, exactly. So if you're told that the angle at the top is, let's say, 20 degrees, then that would mean the two equal angles at the bottom must add up to 160 degrees, right? Because 20 plus 160 gives you 180. And so what must each of these angles be if they add up to 160? So what must each of them be?
80.
Exactly. So you see that all you need to know, if you know that the triangle is isosceles, which means that it's got two equal sides, that means these two angles are at the base are also the same. So then you don't even need to know two sides, two angles and one side. It's enough to know the bottom side, and the angle at the top is enough. You can figure out everything else about that triangle, right? So this is an interesting math fact, that if you have a isosceles triangle and you happen to know the base, and if you happen to know the angle at the top, then this symbol that I drew is just a symbol for an angle. It's the Greek letter theta. So if you happen to know the angle at the top, and if you happen to know the length of the base, you can figure out everything about that triangle, right? You can figure out all the other angles, you can figure out all the other sides, you can figure out everything about that triangle. Now, this is what we are going to use in determining astronomical distances. So how does that work? So the so the method that I'm describing right now is called the method of parallax. So how does the method of parallax work? Well, suppose you are on the Earth over here, and there is some star which is not too far away. It's not as far away as the other stars. Just one second. And there are some stars which are very, very, very far away. So there's a group of stars over here. It's really far away. Another group of stars really far away, right? Now, suppose you're on the Earth and you set up your telescope over here and you're looking at this nearby star, right? So let's call this location A, and let's call uh, another location on the other side of the Earth to be B. So let's say that you're at A, you've pointed your telescope towards the sky, and you're looking at this star which is nearby, right? So to you, this star will appear to be in the background of the group of stars on the left, right? So to you, it would look like the star is in, in the background of this group of stars, right? Now, suppose your friend sets up his or her telescope. Your friend lives at location B on the other side of the Earth, and they set up their telescope at B, and they look at the same star. They're going to see the star in the background of this group of stars. That makes sense? So the picture that you will take of the star will be a little bit different than the picture taken by your friend who's on the other side of the Earth, because your friend has a different vantage than you do, right? So what you can do at that point is that you can put your picture and your friend's picture together, right? Do a couple of calculations, and from those calculations, you can figure out what this angle is. So if you draw a line from your location to the star and your friend's location to the star, and this angle happens to be you can figure out what this angle is by just comparing the picture taken by you and the picture taken by your friend, right? So if you figure out this angle, if you happen to know this distance, this is just the diameter of the Earth. So it looks like we are done. So we can figure out, if we know this angle at the top, and if we know this distance, which is the distance, the separation, or the distance between the two observers, um, this distance is called the baseline. So if you know the baseline, and if you know the angle also has a name. The angle is called the parallax angle. If you know these two, then you can plug them into a simple formula and you can find the distance to that star. And so what is that very simple formula? The formula is the parallax is equal to, the distance is equal to the baseline multiplied by 57.3 divided by the parallax angle in degrees, right? So if you know the distance, if you know the baseline, And if you know the parallax, you can easily figure out the distance from there by just plugging it into this formula. So let's look at an example. So suppose okay, so I have um, let's look at this example. So suppose there are two observers who are 1,000 kilometers apart. So there are two observers, let's call them A and B. They are 1,000 kilometers apart, right? And they're looking at the moon and they measure a parallax angle. The parallax angle is this angle up here. They measure this angle to be 0.15 degrees. The baseline distance is 1,000 kilometers. The question is, what is the distance to the moon? So the baseline distance is given, it's 1,000 kilometers. The parallax angle is given. So all you have to do is just plug into the formula for the distance. So the distance is equal to baseline. I'll just write, okay, baseline multiplied by 57.3 divided by the parallax. So the distance, so the base, what should I plug in for the baseline?
1,000.
Yes, 1,000 kilometers times 57.3 divided by the parallax, which is 0.15. And so if you just work this out, can somebody work this out and tell me what you get?
Uh, 382,000.
Yeah, 382,000 kilometers, and that's that is more or less the distance to the moon. So it's a um, it's a it's a fairly accurate value. So you can see the power of mathematics. So by just sitting on your just by staying on the earth without actually having to go to the moon, and by making a couple of simple measurements, it's possible to find out the distance to the moon, which is pretty amazing. So this is the method of parallax, which can be used to find the distances to objects in the sky. Now, there are some limitations to this method. To understand what the limitations are, let's say, let's just think about what is the largest possible parallax angle you can get on the Earth. Um, so in the previous example, we had two friends who were 1,000 kilometers across on the Earth. But suppose you want to make your parallax angle as large as you can possibly make it on the Earth. And let's say that you and your friend can go wherever you want on the Earth. So what is the largest possible baseline distance you can get on the Earth?
I guess the diameter of the Earth.
Yes, very good. So the diameter of the Earth would be the largest possible baseline distance. So you and your friend would have to stand on opposite sides of the Earth. And then the distance between you two is going to be the diameter of the Earth. And does anybody remember the radius of the Earth? How many kilometers it is? The radius of the Earth is 6,400 kilometers. So that would mean the diameter of the Earth is double that. So the largest possible baseline distance that you can get on the Earth is 12,800 kilometers, right? So that's the largest possible baseline distance. All right. Now, suppose you have an object that's over here, right? The parallax angle is this angle. So you draw one line from this observer and one line from the other observer. The angle between these two at the top is the parallax angle. Now, if the object is further out, will the parallax angle be larger or smaller? What do you think will happen to the parallax angle if an object is even further out?
Will it be smaller?
Yes, it'll be smaller. Exactly. Very good. So let's just see that. So you draw a line like this, and you draw another line like that. And now you can see that the wedge made at the top, the angle made at the top, is smaller than before. So as an object gets further and further and further, the parallax angle gets smaller and smaller and smaller. That makes sense? So that shows you one limitation of this method, which is that once, if an object is truly far away, the parallax angle might be too small for us to be able to measure. That makes sense? So the parallax angle will be way too small for us to measure. So that is why the method of parallax can work for some nearby stars and planets, but it cannot work for stars which are very far away. That makes sense? So you can only use it for the closest stars, and you can use it for the planets and the moon and so on. Okay, so an important conceptual question which I sometimes ask on exams is what happens to the parallax angle if an object is closer or further? And you know the answer. If the object is further out, you can see in this figure that the parallax angle gets smaller and smaller. If the object is closer, then the parallax angle will be much wider, right? And how does the baseline determine the parallax? So what happens to the parallax angle if the baseline is smaller? So the object is over here, the two observers are over here, they're making a smaller baseline. If the baseline is increased, will the parallax angle increase or decrease?
Decrease.
If the baseline is increased, so suppose they move
Sorry,
to
increase. If
exactly, very
increase.
good, yeah. So if the baseline is increased, so if they move to a larger distance, then obviously the parallax angle will also get wider, right? So the parallax angle is the angle at the top. So if the two observers spread out, then they can make a larger parallax angle. So we obviously want the parallax angle to be large so that it's easy to measure, because the smaller the parallax angle is, the harder it is for us to measure. So you can see that the largest possible baseline that we can have is the diameter of the Earth, right? And so that seems to be a practical limitation of our process, because we cannot get a larger baseline if we are on the Earth, right? However, there is one very clever way of getting around this. Does anybody know how we can get a larger baseline than the diameter of the Earth? How would that be possible? Because we want as large of a baseline as possible, and 12,800 kilometers really is not that much. So we want a much larger baseline. So how can we get a larger baseline than that? The answer is by just using the Earth's orbit. So this is the sun. We've seen that in June, the Earth might be over here. In December, or it doesn't matter. In June, the Earth might be over here. Let's say that we are looking at a star somewhere over here, right? Where is the Earth going to be in 6 months later? So in December, the Earth will be on the other side of the sun. The Earth will be over here. So you need to take one photograph of the sky in June, and then you need to take exactly the same photograph of the sky with the telescope in exactly the same location once more in December, 6 months later. And so what you're doing is you're now you have this huge distance as the baseline. Can somebody tell me what is this distance? What is the distance, the baseline distance now?
186 million.
Yes, 93 million is the radius. I mean, is the distance out between the Earth and the Sun. So it's double that, 186 million miles. So that's much better than 128,000 kilometers. Now we can get a baseline of 186 million miles, and that is how you can find that's the baseline that you need in order to be able to measure the parallax of some of the nearby stars, because the stars are so incredibly far away. So that is how you can measure distances to some nearby stars using the method of parallax. You have to take one picture of the sky at a certain time, and then exactly 6 months later take the same picture of the sky, and you'll see that some of the nearby stars have slightly changed position, and by measuring that slight change of position, you can figure out the parallax angle, and from there you can apply this formula that we just learned and find the distance to those stars. So that is how you can apply the method of parallax to find distances. All right, now I'll show you one example of somebody actually doing this. So let's look at this. So some amateur astronomers wanted to, just for fun, they wanted to do an experiment in which one of them was in the UK in a city called Chelsea, and the other one was in Athens, Greece. And these two cities, I think, were separated by a distance of, it says here somewhere, I've forgotten how much it is, 1,000 miles or something like that, probably. So one of them is located over here in the UK, and the other one is located in Greece. And so they decided to take a picture of the moon at exactly the same time. Um, and so and then measure the parallax angle from their locations. The parallax angle means the angle at the top, right? So since they have slightly different locations, you can see that the pictures of the moon that they're taking are slightly different. So look at the picture on the left over here at the top of the screen. So that is the picture taken from Chelsea, UK. And you can see the moon, and you can see the star Regulus, which is that little white spot on the right. And the other picture is taken from Athens, Greece, and you can see that the star Regulus is at a slightly different location. So the position of Regulus will not appear to change because it's way too far away, but the position of the moon will look a little bit different because it's much closer to us. And so if you're looking at it from two different vantages, the position of the moon will look slightly different, right? And you can very clearly see that in these two images. With respect to Regulus, on the image on the left, the moon is moved a little bit to one side, but it looks closer to Regulus in the other picture, which is taken at the same time, but from a different location. So this is what I mean when I said that you and your friend can take pictures of the object, pictures of the sky, and you will see that the object you're photographing will shift a little bit in those pictures, and from there you can figure out the parallax angle. And so this is an example of somebody actually doing this. All right. So that is parallax. That is how you find the distances out to different objects. Um, I'll just mention this one thing because it's really interesting. So we know the size we know the size and the shape of the Earth. The Earth is spherical, and we have a pretty good idea of how large it is now. um, One of the first people to, this was actually not very well known. So people had to be really clever to figure out that the Earth is actually spherical. And some really smart people had figured out that the Earth must be spherical, right? Because if somebody doesn't tell you that the Earth is spherical, you would have no reason to think that it's a sphere, right? I mean, you would just think that it's probably just flat. And a lot of people do think that, unfortunately. The whole flat Earth society, people think that the Earth is just completely flat, which it's not. It's a sphere. Um, Now, Aristotle, we're going to learn a lot about Aristotle in the next chapter. Aristotle pointed out that the Earth must be spherical. And in his book called On the Heavens, which was in 350 BC, so very, very long time ago, Aristotle was able to figure out that the Earth must be spherical. And he gave 4 arguments why the Earth must be spherical. And 3 of these arguments are very good, very clever. The 4th one is wrong. So I'll just quickly go through these 3 arguments because they're really, really nice and really cute. So Aristotle's first argument was gravity. So he had noticed that gravity always tries to pull everything down, right? Um, so he concluded that if gravity is trying to pull everything down towards a common center, right? So what shape do you have which doesn't have any protruding edges? Because if gravity is trying to pull everything down, there's no gravity is not going to allow an edge to stick out, right? So what shape do you have that doesn't have any edges sticking out? It's obviously not a rectangular box, right? So box has corners. So what shape can you think of that doesn't have any edges sticking out? The answer is a sphere. And so Aristotle concluded that because of gravity, the Earth has to be spherical, because gravity is trying to pull everything together. So it will try to make a shape that doesn't have anything sticking out, any edges sticking out. So that was his first argument, which I think is pretty clever and it's correct. Uh, The second argument that Aristotle gave was that he had seen a lot of lunar eclipses, right? And he saw that as the moon is moving into the Earth's shadow always appears to be circular. So a part of a circle, it's an arc. So he asked himself, what shape do you have whose shadow is always an arc of a circle? Uh, and the answer is that it has to be a sphere. A sphere is a shape. If you take the shadow of a sphere, it will always be circular. Or so a part of the shadow will always look like an arc, right? Any other shape will not necessarily always have a circular shadow, but a sphere will always have a circular shadow. So from that, from having watched many lunar eclipses, he concluded that since the Earth's shadow is always circular, he concluded that the Earth must be spherical. And the third piece of logic that he used is he knew that as you travel south along the south, uh, you see newer stars appearing in the sky. So, and we now understand why that's the case very easily. So if you're in the northern hemisphere and you look directly upwards, you'll see some stars in this location. But suppose you travel south and you cross the equator and you go to the southern hemisphere. Now when you look up, you're looking in this direction, right? This is up for you when you're in the southern hemisphere. And so you're going to see different stars in the sky. You'll be able to see stars which were not visible in the northern hemisphere. So he gave the example of the star Canopus. Um, Canopus, he knew, is visible from, Canopus happens to be the second brightest star in the sky. The brightest star in the sky is Sirius. Canopus is the second brightest star in the sky. And he knew that Canopus is visible from Alexandria, but it's not visible from Athens. And so he concluded that, so that also seemed to indicate to him that the surface of the earth must be curved. And so these are three solid pieces of logic that he used to conclude that the earth must be spherical. The fourth one has to do with elephants, and it's not right. So what's the logic over there? So Alexander the Great, I'm sure you've heard of Alexander the Great. So he had conquered most of the world. He had conquered Africa, almost the entire continent of Africa, and then he had conquered his way all the way up to India. Um, and so Aristotle had heard that there are these mighty beasts called elephants that live in Africa, and also there are elephants in India. And so he thought that, but to go to Africa you have to go one way, and to go to India you have to go the other way, right? And you end up with elephants in both locations. So he thought that maybe you're just going around, and so Africa and India are probably right next to each other. That's why there's elephants in both places. But on that point, he was completely wrong, because there is the whole Indian Ocean between Africa and India, and in fact, the elephants in Africa are very different than the elephants in India. The African elephants are much bigger, almost twice in size compared to the Indian elephants. All right. So this fourth point is not correct, but the first three arguments that he gave are very are correct. Okay, we'll skip this. So Eratosthenes was a very brilliant person who lived in 276 to 195 BC, much earlier than Aristotle, and he figured out a lot of things because he was just insanely clever. He was able to figure out that the Earth is round. He was also able to measure the circumference of the Earth, but we'll skip that. Okay. Really the last topic that we're going to cover in this chapter is angular diameter. So let me just quickly explain what angular diameter is. So suppose you are on the Earth right here, and you are looking at any object in the sky, let's say the moon. Now, if you draw a line from your location to one end of the object and another line from your location to the other end of the object, these are imaginary lines that you're drawing from where you are to one end of the object and the other end of the object, then this little angle that you made between these two lines has a name. It's called the angular diameter of the object. So this angle is called the angular diameter of the object. And the angular diameter. Why is the angular diameter useful? It's useful because if you know the angular diameter, and if you happen to know the distance out to the object that you're looking at, which is the moon in this case, then you can use these two pieces of information, and you can actually find the size of the object, the actual diameter of the object. So that's very useful. So if you know the distance out to the moon, and if you can measure the angular diameter of the moon, you can plug those two into a very simple formula, and you can get the distance. You can get the actual diameter of the moon, right? So what is that simple formula? The simple formula is that the diameter of an object that you're looking at is equal to the distance of that object, which you probably know from a parallax, which you can figure out from parallax, and times the angular diameter multiplied by divided by 57.3. So that's the formula. The actual physical diameter of an object is equal to the distance multiplied by the angular diameter divided by 57.3, right? So and just to reiterate, here's a much nicer diagram than the one that I drew. You can see what the angular diameter is. So here is the observer. There are the two imaginary lines which go from the observer to the two ends of the object. And you have the angle between those two lines. That's called the angular diameter. And you can see the distance to that object, right? So the distance and the angular diameter are the two pieces of information that you need. And if you plug them into this formula, you'll get the actual diameter of the object. So let's look at an example of this. The moon's angular diameter, it's sometimes the angular diameter is also called the angular diameter distance, but I'll just skip that. So the moon's angular diameter is 0.52 degrees. Given that its distance is about 380,000 kilometers, find the actual diameter of the moon, right? So this is an example of a question that you might see on tests and quizzes. So basically what's it saying? So this is the observer, this is the moon. You're given the angular diameter. Oops, make the moon a little larger. You're given the angular diameter. The angular diameter is 0.52 degrees. And you're given the distance to the moon. It's 380,000 kilometers. And from there, you want to find out the actual diameter of the moon, this distance, right? So all you have to do is just plug into the formula. So diameter equals distance multiplied by angular diameter divided by 57.3. And so you just need to plug in the distance, which is 380,000 kilometers, multiplied by 0.52, that's given, divided by 57.3. Can somebody work this out and tell me what you get? Yeah,
3,448.52.
very good. So 3,448. And that's the diameter of the moon. That's a pretty good estimate of the diameter of the moon. So you can see how powerful math is. Like just sitting in your chair and with few pieces of information, you were able to measure the physical diameter of the moon. So how the size of the moon, you were able to figure that out. It's 3,448 kilometers. Now you might think that, okay, how would I find out the angular diameter? How would I measure the angular diameter? That's actually very easy to do. You don't even need any sophisticated equipment to do it. There are instruments which will measure it for you very accurately, but it's very easy to just make a ballpark estimate of the angular diameter in degrees. So how do you do that? You can just use your hands and fingers. So if you make a fist, and so if you make a fist like this and hold it, like stretch out your arm in front of your face, then the fist, the width of the fist is 10 degrees, right? So your fist makes a 10-degree angular diameter. If you hold out your pinky at arm's length, your pinky makes an angular diameter of 1 degree. That makes sense. So if you are ever looking at the full moon and you want to figure out what the angular diameter of the full moon is, so all you have to do is see if hold out your pinky at arm's length and see if it covers up the moon. So if it covers up the moon, if it blocks the moon, that means it has the same angular diameter as the moon. And so that would mean that the moon that day has an angular diameter of 1 degree. You can also make an estimate, like if you find that the moon, your pinky covers up about half of the moon, that would mean that the moon that day has an angular diameter of 2 degrees, because your pinky makes an angular diameter of one degree. So by just using this diagram as a guide, you can measure angular distances just using your hands and fingers. Okay, but there are instruments which will measure it for you accurately. All right. Um, let's try this example. Let me see. And we are pretty much done with chapter 1. Let's see. Uh, yeah, this one. Okay, so let's try this problem. So what happens to the angular diameter if an object is further away versus if it's closer? Does the angular diameter increase or decrease? All right, please put in your answers. Okay, so yes, the further away the object is, the angular diameter will decrease. And just to make sure that we are all on the same page, so if you, let's say that you're looking at the angular diameter of this object when it's, and you're looking at it from here. So angular diameter means you draw one line from your location to one end of the object and then to the other end of the object. And this angle is going to be the angular diameter. But suppose you move the object further out, or you move yourself further out. You don't have to draw another sphere then, another circle. Now, let's see what the angular diameter is. Oops, what is that? It's crazy. Okay. So if you're looking at it from further out, if the object is further away, you can see that this wedge here is much smaller. So the angular diameter gets smaller if the object is further out. All right. So that concludes chapter 1. So as I mentioned at the beginning of today's lecture, we are going to have where is the beginning of today's lecture? Yeah, so we are going to have our first timed quiz this weekend, and it will be based on chapter 1 because we've covered all of chapter 1. And so to prepare for all of my timed quizzes and exams, it's a good idea to go over the lecture, make sure you understand everything that's been discussed in the lecture, read the relevant sections of the textbook. If there is something that is in the textbook which I haven't touched at all, then you can skip that. But read the relevant sections from the textbook, and basically, and all math problems, just make sure that you fully understand how I did the math problems during the lecture. If you understand the ones that we did in class, you should not have any trouble doing ones on the quizzes and exams, because I don't like to put any surprises. So I put in very similar questions to the ones that we have done in class. Not exactly the same, but very similar questions to the ones that we've done in class. So yeah, so that'll be timed quiz 1. Any questions about chapter 1 or the upcoming timed quiz? All right, so if there's no questions, then I'll just end the session for today, and I'll see you all next week. Okay, bye.
All right, thank you.